So good afternoon and welcome to this fourth session of this workshop. This is on model evaluation and extraction datasets. We have three interesting papers scheduled in this particular session. The first paper is titled An Empirical Evaluation of Adversarial Examples, Defenses and Robustness Scores, and it will be presented by Rudolf. Rudolf, are you there?
Yes, can you hear me also?
Yeah, we can hear you.
Great.
And
do you see my screen already? Perfect.
Yeah, we can see your screen, and we are going to start the recording. So it will be for about 15 minutes and then 5 minutes Q&A. Okay, please go ahead, Rudolf.
Okay, thanks for the introduction and welcome everyone. I had the pleasure to open the first session. Now I have the pleasure to open the last session. I hope next year I can participate in person. This is a presentation where we looked a bit into adversarial examples and especially defenses against it. And then we also wanted to figure out if there is a relation to robustness scores and to one specific robustness score that would be model agnostic. The motivation for our work is basically, as we've heard a few times in this workshop, machine learning becomes more and more powerful, more and more used. So also the potential threats to machine learning become more and more interesting or more and more relevant, because we need to defend against vulnerabilities, and there are certain vulnerabilities, especially for deep learning. And if this could turn into safety critical issues as well if the machine learning system fails, autonomous vehicles and things like this. The threat model we are specifically looking at this time, so it's an evasion attack, similar slide that I had in my first talk. So we're looking at evasion attacks happening at the test time, at the prediction time, and we basically look most specifically into, again, integrity attacks. The attacker is capable to manipulate the test data that is going to be processed by the system. And we assume that the attacker, for most of the attacks that we use, has a white box access, but we also look at a few black box setting. And basically what we wanted to investigate also here a bit in detail is to check, on the one hand, if there's specific patterns that certain defense mechanisms would work well against certain types of attacks, also for given data sets and given machine learning models. So we looked at different well-known architectures. And then we wanted to improve the detection by combining some of the existing defense methods. And the last thing was to test if there's a relation to a robustness score, which would basically allow you to upfront, without any specific test samples, evaluate or guess how robust the model would be. So this would be the ideal setting if this would correlate. The robustness score we specifically used is the so-called clever score, which is basically a score that is model agnostic. So it's not specific for one model type, but it should work across different types of models. And it's also a metric that is feasible to compute for large neural networks, even though feasible still means that some of the scores can take a really long time to compute, but it's more feasible than other ones. And it would basically allow to compute a lower bound for the minimum distortion that would need to be done to fool the model. And this quite complicated name comes from the Lipschitz constants that needed to be used there. We're not going to describe the whole approach in detail. There was a paper from some colleagues on ICLR 4 years ago that describes this in detail. But basically, the motivation here is that using extreme value theory, you can actually estimate this score or this robustness quite efficiently with a lower number of samples. So with actually a feasible number of samples. We tested our attacks and defenses on two different data sets. The well-known Cypher data set, Cypher 10. I don't think I need to describe too much about it. On this one, we basically tried primarily two different types of models. One, a ResNet 18, which achieves very high scores in prediction, and then also one version that we adversarially trained on it. And then we also evaluated on ImageNet, where we basically used pre-trained models, because training on ImageNet, of course, is quite time-consuming, and it's also quite difficult to get better than the pre-trained models already. So we used the free pre-trained models, the version 3 from Reception, MobileNet, and ResNet 50. And then we basically were evaluating the attacks on the test set or on the validation set that's normally provided with the large-scale visual recognition challenge. We evaluated a total of 7 attacks, some very well known as the fast gradient sign method, the projected gradient descent, and also Kalinin and Wagner, which is one of the most powerful attacks because it produces very small perturbations. And then we also looked at universal perturbations, where you don't compute the perturbation per image, but just once for the whole network. And we also had one black box attack called hop, skip, jump. So this is an attack that does not need information about the learned model parameters and the gradients, but basically just works with the output. We applied 4 different types of defenses. On the one hand, adversarial training. This was mostly done for Cypher 10 for performance reasons, because it's quite time-consuming to retrain ImageNet. And then we use basically different types of pre-processing methods that pre-process the input. So we use spatial smoothing, JPEG compression, and total variance minimization. And we evaluated 3 settings for the attack. So the attacker wants to have a targeted attack to force a specific class. And here we check simply the next class in the class index, which is very often used. Or we also check the more challenging task that you want to actually change it to the least likely class from the original prediction. And then also untargeted, which basically means just any other class, which is normally the easiest to achieve. And relied on implementations from the IBM Adversarial Robustness toolbox. I'm just going to present a few results because we don't have that much time here. And there's also a lot of plots otherwise to digest, but there's more details in the paper. Basically, what you can see, of course, this is now for Cypher 10 without any pre-processing, and you would have 2 different models. Blue would be the normal model, and orange or red, not sure how it comes across on the projector, is the adversarially trained model. So where we generate adversarial examples and then feed them to the model to retrain it so that it would learn how to protect against these adversarial examples. And not surprisingly, the untarget setting is the easiest. So most of the attacks work very, very well with almost 100% or exactly 100% correctness in the untargeted setting. But the other 2 settings are a bit more difficult. So the targeted and the targeted least likely and targeted next class, they're a bit more difficult to achieve perfect results. Some things that were quite interesting is that in some settings, you would expect normally the adversarial trained model to actually perform pattern. And this happened in some cases, but in some other settings, actually the adversarially trained model was then, when you generate new examples, not well protected, or even worse than the unprotected version. When we apply various types of pre-processing defenses, such as total variance minimization, JPEG compression, we can see that for many settings, we're able to reduce the attack rate. So the lower the bar here, obviously the better for the defender. In this case, we are now the defender. We would see also slight differences against which attacks these 2 defenses work. And this is actually something that is good, because that is something we can exploit. If they would defend against the same types of attacks and maybe the same images even, then there would be no potential for combination. So this is a good feature. And we see that against some attacks, the reduction with these very simple pre-processing methods actually works quite well. Interesting, for example, JPEG compression works very well, for example, against the Kalinin and Wagner method, which is one that introduces a very small perturbation in the image. But against this defense, then is also, at least in the non-adaptive attacker mode, not very efficient anymore. So we can then, for example, combine these 2 methods, total variance minimization and JPEG compression. Now the plot might be a bit confusing because we have now a different scale on the axis, but as you would see compared to before, where we had, for example, for the auto-PGT up to 15% success chance. Here we reduced this a bit, and also for all the other methods, we're reducing the success rate by combining these two methods together. There's many more combinations that you can, of course, try. This is just one example. Not all of the combinations are successful, but there are quite some that can improve over single versions. For ImageNet, we did basically the same experiments. And again, we have here the 3 different cases. And again, not surprisingly, the untargeted attack is the easiest, because you just want to go into any of the other, in this case, 1,000 classes, while the next class is really the one really in the next class index, which is sometimes also a class that is very similar, because in ImageNet you have many classes that are quite related to each other. So the next class might actually be one that is quite similar to the original class. And least likely, again, is the one that is the most difficult setting, because you need to actually perturb it to achieve the class that was in the beginning the most unlikely, and they should now become the most likely class for prediction. What we can see here also that, for example, for the targeted attacks, for the targeted settings, many of the attacks on ImageNet are not successful, especially the black box attack, but also the shadow attack. They are not, they don't work well here. The only difference you can see between these two is actually basically the amount of perturbation that's needed to be done. So the smaller bars, this is here the amount of perturbation that is needed. And you see that this is quite a large amount of perturbation. For example, for the fast gradient sign method, for almost no success rate at all in the least likely setting, you need a lot of perturbation. And in the targeted next class, this is actually a bit easier. And then for the untargeted, you need the least amount of perturbations to get a relatively high success rate. Similar setting here, various defenses manage to reduce success rates of various attacks quite significantly. For example, again, the Kalina and Wagner method, which was one of the only ones, or the only one that was actually successful initially, manages to reduce the attack success rate quite well for most of the models. Maybe not so much for Inception and ResNet on the with the infinity version of the Kalina and Wagner method, but it's still a very, very small success rate. Interestingly, the other attacks, they were already not successful before, so also defense at least didn't harm and didn't make it worse. Again, the combination of various types of defenses, so here, for example, against spatial smoothing and Chebeck compression combined, normally manages to reduce the attack rate better than single defenses. This is now against the untargeted setting, where you see actually quite a lot of reduction from almost 100% initially to, in some of the attacks, you get to, I don't know, 20 to 30%, up to 40% for many of them. It's a success rate. Some of them still stay very successful. So, for example, auto-PGD, the projected gradient descent, doesn't really reduce much ineffectiveness by these defenses. And the last thing that we looked at, and this is a very big table to look at, it's described maybe a bit more in detail in the paper, but we wanted to check if there's a correlation between these scores, the Clever score, and the empirically measured attack success rate that we had evaluated. And there's a few settings where this actually has a value, and you can actually learn something, or you can actually make some predictions about the success rates. For example, the scores of the adversarial trained networks, there were most of the settings are better than for the ResNet itself, for Cypher in this case, which is what we would also hope for, because the adversarial trained one is more robust against the attacks. But in general, we see that already for the simple, not adversarial trained ResNet, the scores are quite high, and they're not that much smaller than for the adversarial trained ones. So they're a bit too high, and they actually give maybe a false sense of robustness. And with the defenses, actually both models, adversarial trained or not, they're actually quite similar in the measured success rate of the attacks, but this is only partially reflected in the score. So the scores don't really reflect this. Sometimes it will predict that one of the models would be significantly more robust than the other one, than it actually was empirically measured. And we can draw similar conclusions also for ImageNet. Here I show ImageNet against fast gradient sign method. And in principle, for most of the defenses, the score increases compared to the baseline, which is good because this is what we expected and also measured. If we apply the defenses, the attacks are less successful. But it's actually not well predicting this for the combinations. So the robustness scores for the combinations actually is lower, even for the measured success of the defenses also gets lower. And also the untargeted settings show too high scores than what the untargeted success rate actually was resulting into. So as a conclusion, the best defense against various attacks is really, unfortunately, very case specific. There is a maybe one observation is that the pre-processing defenses actually work better against stronger attacks. This sounds a bit counterintuitive, but stronger in this case measured being introducing less perturbation, which also means that this little perturbation maybe is easier to remove by this pre-processing method. The combinations can improve the defense rate for quite many settings, and we were able to achieve that. Unfortunately, the exact combination on which one is working the best really depends on what model and what data set you're working on. But in most settings, at least the combination wasn't worse than the single defense. So applying combinations at least doesn't cost you much. And as it has been seen in the results also before, the clever score doesn't really correlate very strongly with the empirical measures, which is a bit unfortunate because we could use this otherwise to really upfront estimate how robust the model is going to be. But that didn't provide any conclusive result in our experimentation, at least in the cases we had covered. So with quite many attacks and with quite a few defenses, this didn't really show any reliable, predictable pattern. Okay, good. Then I hope I was mostly in time, and I would be happy to answer any questions.
Thanks very much. Is there any question from the audience here in person? If there is no question, is there any question from the online participants? Okay, if there is no question, Rudolf, could you please go to your slide number 14? I had a clarification
14, yes.
where you have the graphs.
Yes.
Yeah, so here I see that you have resonate 50, both in greens. Is there a typo there, or I was a little confused?
So you mean that on the left and on the right it means resonate 50?
So in the bottom figure, you have resonate 50
yes.
repeated.
Yes. So maybe I was not clear on that. Basically, on the left axis, you see the success rate. On the right axis, you see basically the perturbation that was introduced, measured in the L2 norm in this case, and the slightly more opaque color, so the slightly less strong green is the perturbation that was needed. So you see actually how the perturbation that was needed changes and actually increases, for example, for the universal perturbation, which on the right hand here you had, I don't know, at 5, I don't know, at 10 or something, I guess, needs to increase to a higher value also here. So yeah, maybe this was a bit, maybe I didn't explain this well, but yeah.
Okay.
Rudolf, I have one question. Is there a similar study for, other kinds of data, say text data, or maybe you have done a study on text data?
We haven't. And in general, evasion attacks for text has been mostly used for spam evasion, for example. There's been some studies longer time already, because this is actually how most of the evasion attacks actually started longer time ago. I don't know if there's any, any bigger comparative study that was recently done. And I don't actually know what are the defenses you would apply in text, unfortunately. Yeah, sorry.
Thank you.
Okay, so let us thank the speaker.
Yeah.